So now let's start chapter 6, thermal oxidation. The idea is very simple. So we have the silicon. And react with oxygen at high temperature about 7 degrees to form silicon oxide. Another possibility is that this water is oxygen replaced by the water molecule. This is the dry oxidation. This one is called the white oxidation. So now let's look at the property of the thermally grown silicon oxide. For the thermal oxide, first it is amorphous, stable and reproducible and conformal growth. So conformal means the growth rate along the vertical direction is the same as the growth rate as the horizontal direction. So the growth on all the surface has the same growth rate. So the melting point for the amorphous silicon oxide is 1,700 degrees. But even at this high temperature, it is still very viscous. It's very viscous, not like a water that very flow well, but it is very viscous at this temperature for the amorphous silicon oxide. So density is 2.21 gram per cubic centimeter, so almost the same as that of silicon. For the single crystal silicon oxide, this is called a quartz. This one has higher density, so 2.65 gram per cubic centimeter. So now let's look at atomic density of the amorphous oxide. It's given by this number. How to get this number? So we know that 1 mole silicon oxide equal to 60.8 gram. So now we look at 1 cubic centimeter. So 1 cubic centimeter equal to 2.21 gram. Then 1 mole. So 2.21 divided by 60.0.8 is equal to this many mole. So 1 cubic centimeter equal to this many mole. So then we times our gradual number. Then you get this number. So this number times this number, so you get this number. So the index n equal to 1.46. A Dirichlet constant equal to epsilon equals 3.9. Normally we know that n equals to, for the non-magnetic, for the normal material, n equals epsilon square root of epsilon. So you can, but for this case you can see the threshold square root not equal to 1.46. Why this is not right? So this is because this index here is for the visible light. Visible light, we know the frequency is 10 to the power 14 Hz. This is for the visible light. But for this one, this is for the DC. So it's different. This is for the DC, and this is for the very, very 10 to the power 14 Hz. So amorphous silicon oxide has very excellent insulator. So we have the resistivity 10 to the power 20 ohm centimeter. For the silicon, so normally moderately doped silicon has 1 ohm centimeter. For the metal, like a gold, it's 10 to minus 6 ohm centimeter. So this one is 10 to the power 20 ohm centimeter. And a breakdown voltage is 10 to the power 7 volt per centimeter equal to 1 volt per nanometer. This is the breakdown voltage. So this is the silicon and the thermal oxide interface. Because this is the silicon, this is silicon oxide. You can see that interface is very, very clear and very well defined. So this is the main reason that the perfect interface between the silicon and the silicon oxide is one major reason that the IC we use the silicon. We use silicon rather than a silicon germanium. So germanium was replaced by silicon in the early 1960s. From chapter 2, we learn about the local oxidation for the isolation. For the isolation between NMOS and the PMOS. So we grow oxide to isolate NMOS and the PMOS. So the idea is like this. So we have silicon. Here we have a little bit oxide. This 10 nanometer oxide will not affect anything. Then we have silicon nitride. This is the mask. Then we grow the silicon oxide. So we have in the end get something like this. So we have this silicon oxide. Here is also silicon oxide. So we have this lateral extension. So this is called a brush beak. You can see the same thing here. So here's the silicon. Here's the silicon nitride mask. So we have a lot of lateral growth. So this interface here, this is the original silicon surface. So during the growth, the silicon gets consumed and also gets expanded from both sides. So this lateral birch beak will take a lot of space. This is a problem because this takes a lot of space. You cannot put so many transistors. So to solve this problem, the one way is to have the recessed process. So here we have the mask. Then we etch into the silicon a little bit. Then we grow the silicon oxide. This way, the lateral growth will not be too much. A better way is to etch deeper. Then you do the LPCVD. Then we use low pressure chemical vapor deposition to deposit some silicon oxide to fill this area with the deposited silicon oxide rather than a thermal oxide. This way there will be no lateral growth. So you just fill in the oxide, no lateral extension. So here is the basic oxide structure. So we have the silicon atom here, and we have 4 oxygen. Each of the oxygen here. So each of the oxygen here is shared by 2 silicon. For example, you can see this one is shared by this silicon atom and this silicon atom. You can see the same thing. So each oxygen is shared by 2 silicon atoms. So this is the single crystal. Single crystal is periodic. So amorphous has no long-range ordering. So actually, this is the quartz crystal structure for the quartz, but actually the crystal structure is quite complicated. So I will show you. So this is the Wikipedia for the silicon oxide. So you can see here. Yeah, you can see. So there is a crystalline form. So this is alpha cross. So this is a crystal structure. There is base cross. This crystal structure. But there are many other forms. They are all single crystal silicon oxide. So you can see they have all different. They have all different configuration. So there are 2 types of oxide. Which is called a white oxide and a dry oxide. Dry and a white oxidation. For the dry oxidation, so we use oxygen. For the white oxidation, we use water. So then we generate some hydrogen. The temperature is about 900 to 1200 degrees. So white oxidation is about 10 times faster than the dry oxidation. So we will see this later on. So the dry oxide, because it's slower growth, usually it's good for the thin oxide, very thin oxide. This is better film quality than the white oxide. So white oxide gives 10 times faster, so you can grow up to a few micrometer thickness. But this is still a good insulator. It's better than CVD oxide. So the white oxide is still much better than the low pressure chemical vapor deposition CVD or PCVD. A plasma enhanced chemical vapor deposition. So the white is still better than other deposited oxide. But this is good for the thick oxides, for example, like for the fused oxide or the masking purpose. At the room temperature, the silicon in the air also creates a native oxide, but this one is normally 1 to 2 nanometer. So if we remove silicon oxide by HF at the room temperature, so after about maybe 1 hour, after 1 hour in the air, it will grow 1 to 2 nanometer. But this one has a poor property, poor insulator, but this can impede surface process of the silicon. So when the silicon is oxidized, the volume expands by 2.2 times. So here you can see here. So this is the original surface here. So when the silicon got oxidized, so 0.46 oxide, this is oxide thickness is below the original surface, and 0.54 is above the original surface. So here you can see this number here, 0.46 is this number here, 0.46. This is the volume of the silicon over the volume of the silicon oxide. So here we can calculate. So we want to know the thickness of silicon and the thickness of the silicon oxide when during this process. So the molar volume ratio between the silicon and the silicon oxide, because 1 mole silicon will give 1 mole silicon oxide. So we can get the volume for 1 mole of silicon and 1 mole of silicon oxide. For 1 mole of silicon, the volume is given by molecular weight. So 1 mole is 28.9 grams. the density is 2.33 gram per cubic centimeter. So this is the volume for 1 mole. The same thing for the silicon oxide. Then we get this number, 1.46. So the reverse, 1 over 1.46 give you this number. So this is the volume expansion. For example, if I ask you, if we have a silicon cylinder, so when this one is oxidized, so how big, when it becomes a silicon oxide, how big is the diameter or is the radius? So you can use this one, the volume expansion. You can see pi r squared equal to 2.2 times pi r prime squared, something like this. This for the cylinder. You can do the same thing for the hose. If this is the silicon, you can calculate how much oxide grow you can fill in. You can have all filled with the silicon oxide. So you just need to use this volume expansion 2.2. But for the case of the 1D growth along the z direction, this volume expansion is the same as the thickness expansion. So now we look at manufacturing method. So we use the furnace. This is the same thing as the LPCVD. So normally, for this one, for example, we have the furnace can do different things. This may be oxidation. This may be LPCVD, silicon, polysilicon. This one may be LPCVD, silicon nitride, or maybe a silicon oxide. So you can see, so the furnace for the oxidation is the same as the furnace for the chemical vapor deposition process. But this is the horizontal furnace. This is the vertical furnace. So we can do the dry oxidation with oxygen. This is for the purge. So nitrogen is for the purge purpose. For the wet oxidation, we can have the oxygen flow through the water, then they come out. This one will contain oxygen plus water. But the water is much more efficient in oxidation process. But this dominate. So the third type is called a pyrogenic oxidation. So for this one, the water can have some impurity. This one is heated. There is some contaminant in the water. But when we use pure hydrogen gas and oxygen gas, they will react to form the water. But then this water will be pure. This is called a pyrogenic oxidation. But nowadays, this one is more popular than this one. So here is the photo. You can see we can put the wafer vertically. Like what we do in the LPCVD process. But this is more efficient. We can grow the oxide on like 100 wafers per run. So why we can do this? Because normally the oxidation is done at 1 atmosphere pressure. You know, when we have 1 atmosphere pressure, there's very high pressure. So the gas transport, mass transfer, is much faster than chemical reaction. It's much faster than chemical reaction. So the growth rate is limited by the chemical reaction. So as long as we have the chemical reaction, it depends on the temperature. So as long as we have uniform temperature along all the wafers, then we got the same growth rate. That's why we can put the so many wafers, and we use this one, the hot wall. So we use the resistant heating to heat the many wafers at the same time. Now let's look at the measurement tools. So first one is called a deck tag. So deck tag, we use the stylus scan along the surface to give something like this. Then you know, this way you can know the height, how many nanometers. So the accuracy for this one is about 1 nanometer. So it's pretty accurate, 1 nanometer accuracy. So now, how to make the step? How to make the steps for the measurement? So we can use hydrofluoric acid. We can use HF to make the step. For instance, if this is silicon oxide, and this silicon, what you can do? You paste. So you paste some photoresist. Then you use HF to add away the silicon oxide. Then you remove the photoresist. This way you get a step here. So once you have the step, you can use the deck tag to measure the thickness of the silicon oxide. So the second way, we just look at the color. So you know that when the light comes to the thin film, there will be multiple reflection and transmissions. So you can do many more. reflection and transmissions. Then I will look at here. I will add here. You can see a certain color. This color can be calculated. This one is complicated. So when this phi is not equal to 0, so which direction give you the color is complicated. But when you have the phi equal to 0, you have something like this. So silicon oxide, here silicon. So the light come in, come here, and go back, or come out. Then reflect it back, come in and come out. Reflect back, or come in and come out. So we want all the light here to be in phase. But that means the round trip. This round trip, come here. But this round trip equal to 2 times n times the thickness x. This one equal to k lambda. The round trip 2n is the index of the oxide, x is the thickness, equal to k lambda. Then we see the color. But normally we take k equal to 1, then we get this formula here. Here. For example, if we look at I equal to 1.46, so 1.46, lambda equal to 1. For the yellow color, if we talk about 200 nanometer here, then 200 equal to lambda over 2 times 1.46. This gives you 580 nanometer. The lambda equal to 580 nanometer. This one give you the yellow color here. So by looking at the color, you can tell roughly what is the thickness. But this one is not unique. For example, this one is yellow color, but this one is also yellow color. So our eye can tell the color difference between 10 nanometer thickness difference, between two films having 10 nanometer thickness difference. A more accurate way is use the ellipsometry. I think maybe you have learned about ellipsometry. This is the optical method. So we have the light source, and we have the filter, we have the polarizer. So after this polarizer, we get a linear polarizer of the light. So we get linear polarizer of the light. Then we have this one called a quarter wave plate. After a quarter wave plate, this linear polarizer of the light will become circularly polarized of the light. Then a sign on the wafer then gets reflected, and this one is the analyzer. This is analyzer is also a polarizer, but this one is the rotate. You can rotate the polarizer. This way you can find out what is which angle. So you do the rotation. You know which angle give you the maximum and the minimum. Which angle, when you do the rotation, you know which angle give you the maximum and the minimum light intensity. So from those two angles, you can calculate what is the thickness. You do some curve fitting to get the thickness and also get the refractive index n. You can get those numbers. So in modern instruments, so we can do multiple wavelengths and multiple incident angles. This way we can measure complicated film. We can measure a film multiple film stacks. We can get n and the t, n index and thickness for the multi-film stacks, or we can get the n as a function of lambda. For example, you can get something like this. So this is our result. So this is the measurement of amorphous silicon by the PCVD, so plasma enhanced chemical vapor deposition. So we use the ellipsometry in campus. We can measure the n and the k. So this is n. This is the n is the real part of the index, and this k is the imaginary part of the index. So we know that. So normally for your material, so we have here something like this: n equal to n plus I k. So this one give you this is the imaginary part. This corresponds to the absorption of the light. For the transparent material, for the silicon oxide, which is a transparent, for the k equal to 0. So now let's look at a model for the growth of the oxide. It's called a dual groove model. It is also called a linear parabolic model. But this one is developed by the Dio and the group in the I think in the 1968, something like that, near 1968. So the Dio groove is called the Dio groove model. So this is the groove, this is the Andrew groove. So here is the time magnetism month of the year for the 1997. So he worked for the Fairchild semiconductor. If you remember from chapter 1, so Fairchild is the Fairchild is the kind of the founder of the Silicon Valley. So all the big names for the Silicon Valley companies come from the Fairchild. So this group, Andrew Groove, so he is the fourth employee at the Intel. He became the president in 1979 and the CEO in 1987 and the chairman in 1997. So you can see, so he led Intel for more than 20 years. But during his leadership, so Intel had big growth from the memory chip company into the world dominant producer of the microprocessors. But during his tenure as the CEO, there is 45 times growth for the Intel, so making it the world's most valuable company. But today we know this is no longer the case. So here, the Intel shifted from memory chip to the processor because the Japanese in the 1980s. So the Japanese company, they make much better memory chip, but Intel has cannot compete with the Japanese company, so they shifted to the microprocessors. So later on, there is the war, not a war, actually, it's a trade war. But there is a trade war between the Japan and the American, between Japan and the US. So that the Japan cannot win against the US. So the Japanese company they get kind of destroyed by the trade war. So this American company they grew very fast. So here is the 20 years. So because he had been the president, he had been a leader for so many years. So he can propose something for the long term. But nowadays we know that the Intel is about half TSMC. The market value for the Intel is about half of TSMC. There is the Taiwan Semiconductor Manufacturing Corporation. The Taiwan Semiconductor Manufacturing Corporation. But this is the biggest foundry in the world. Like in the iPhone, Qualcomm, everybody they go to TSMC to make their chips. So one reason is that for Groove, so he has the technical background, so he can he pay more attention to the technology. But later on, the CEO for the Intel, they are more maybe economics, business, those kind of background. So they want to have some short-term faster growth, but they do not. They are not so good for the long-term growth of the company because this is the nature. For the people from technology background, they pay more attention to the technology itself. So this is called a linear parabolic model is for the 1D oxide growth along that direction from unpatterned wafer surface. But this one is good for this temperature range, a pretty high pressure, 0.1 to 25 atmosphere pressure, and for the thickness, 20 to 2 micrometer thickness. So the first question, so does oxygen get into the silicon, get in or silicon get out for the reaction? But there are two possibilities. The one possibility is oxygen get through this silicon oxide. We have chemical reaction here. Another possibility is the silicon diffuse out. We have the chemical reaction here. So this one we use the radioactive tracer. It was found that oxidation proceeds by inward movement of oxygen molecules through this silicon oxide to the silicon oxide interface. That means this is the case. Oxygen diffuse from the atmosphere through this oxide come here for the reaction. So this is different from the copper. So for the copper oxidation is the copper move out. If this is the copper oxide, then the copper move out. So we have the chemical reaction here. The same thing for the anodic oxidation. This is the electrochemical oxidation of silicon. This is also the silicon moves upward. So now let's look at let's derive this Dio groove model. So here we talk about the flux. So flux is the number per square centimeter per second. Number per square centimeter per second. So here, C is the oxidant concentration number per cubic centimeter. So the oxygen of water molecule. So first, this is the main gas flow. Then come to the surface. Then get dissolved inside the surface. Then diffuse through this oxide film. Come to the surface of the to this interface. Then we have the silicon oxide formation. So we have three fluxes. The first one is the gas diffusion, the F1. Gas diffusion. Then gas phase transfer. Then we have this the solid state diffusion through this oxide. So this is F2. Then we have the chemical reaction. This is the F3. So in the steady state, so the three fluxes should be the same. And now we look at the flux one-to-one. First one from here to here, the transfer from here to here. But this one is proportional to, you can imagine, Cg minus proportional to the Cg minus Cs. This is for the F1. So F1 is proportional to the Cg minus Cs. So Hg here is the mass transfer coefficient, unit centimeter per second. We know that for the ideal gas, the PV equal to nkt, so also equal to nRT. So this is the mole. How many mole? This is N is the atom number. This is Boltzmann constant. This R equal to 8.31. So from here we know that C is given by definition N over V, number concentration equal to P over KT. So this way we convert the concentration to the pressure. So the pressure we know is easier to measure. So this is what happened on the surface here, outside. And now we want to know inside. This what is O? So this one is given by this called the Henry's law. Henry's law says that so the concentration of the gas species dissolved in a solid is proportional to the partial pressure of that species at the solid surface. So C0 equals HPS. H is the Henry's constant. So this is different for different materials. Then we rewrite this one. So F1 equal to Cg minus Cs. Cs given by Ps over Kt. So equal to Cg minus Co over H. So Ps here is C over H. Then Co over H over Kt. So now we define H is given by Hg over Hkt. So then this is what we also define this one. C star equal to Hkt Cg Hpt. But that means so Cg here. So from here you know the Cd equal to C star divided by Hkt. So Cg is this by C star over Hkt. This by the C0 over Hkt. And then you put the Hkt here. You put Hkt here below Hg. This is given by H. So in the end you get this formula here. But this is the easier way to have the formula. So now let's look at the second term, diffusion. The diffusion is driven by the concentration gradient. So when we have the concentration gradient, so we have the diffusion. So it's proportional to the concentration gradient. But that means it's proportional to maybe C0 minus Ci divided by the thickness x0, x. This is the concentration gradient. So we put a number d in the front. It's given by d C0 minus Ci divided by x. So x is oxide thickness. So the effective, the d is called the diffusivity, oxidant diffusivity. So the diffusivity for the oxygen and the water is similar, about 5 to the power 3 micrometer square per hour at this 1100 degree. So the third flux, this one, F3, is the chemical reaction. So this one is proportional to Ci, it is given by Cs over Ci. But in the steady state, F1 this should be the same. So we know F1 equals this one, and F2 at here, and F3 at here. So we have two equations. To solve two unknown, which is the C0 and the Ci. So this one is unknown, and this Ci is also unknown. So here, how to do this? So first we can think we set F2 equal to F3. So we have minus x equal to KSCI. So this is one equation. Then we can set F1 equal to F3. So we have H C star minus C0 equal to KSCI. So this equation here and this equation here, you can solve C star and C0. The C star, sorry, CI. The CI given by this formula here. Then this one, normally H is much bigger than the chemical reaction. The region is here. So the region, you can see the H is here. H corresponds is the transport at the gas phase. So this gas phase diffusion is super fast. The gas phase transfer is very, very fast. Because the pressure we talk about is like 1 atmosphere. So we know that for the normal LPCVD, so the evaporation gas, the pressure is about 1 torr, which is 1 over 760 atmosphere. So this one here we have very, very 1 atmosphere pressure, very high pressure. So when we have this very high pressure, so the gas phase diffusion, the gas from here to here is really very, very fast, much faster than other processes. That means this H is very big. So this H is very big. So you can see H is much bigger than HKS chemical reaction. So we can ignore this term to have this one. Then C naught is given by this one. Again, we ignore this term equal to C star. So this means the gas absorption rate at the oxide offset. This is the after surface is much faster than chemical occurring at the silicon and silicon oxide interface. Then there are two possibilities. The first is this term. Now we talk about this term here. This term is much less than 1. Then we have this Ci equal to C star. So we have this one. We have nearly flat. This is called reaction rate limited. So Ks is much smaller. The opposite case is the Ks is much bigger than the diffusivity. Then it becomes diffusion limited. In this case, the diffusion from here is thick oxide. This one you can see is thin oxide. For the thick oxide, when the X become bigger, for the thick oxide, we have the diffusion limited. So they have very, very big slope. So the boundary condition between the two situations is given correspond to 50 to 200 nanometer thickness. So now we look at the back again. So you can see in reality we can ignore this term. So we can assume C naught equal to C star. So you can see this one equal to, they are the same thing because H is too big. But we can make this one is the same as this one. So actually we can ignore this term. We can just use F2 and F3. We get the same result. You can see if you take the C0 as the C star, then you get the same result. But this complicated way is derived by by those two persons. Now we still follow their derivation. But in reality, if you want to be simple, you can just take F2 and F3. You ignore F1. You get the same conclusion in the end. So now we have the flux. So now we look at the deposition rate. We need to know the oxidation rate. How many micrometer per hour? So this is what we know. How many micrometer per hour? And then we need to know the N1 value. So N1 is the number of oxidant molecules incorporated per unit volume of oxide growth. For the dry oxidation, for O2, we know that HIO2, this is O2, this is also O2. But this number is given by 2.2 10 to the power 22. So we need, this is because we have this number of citric oxide molecule per volume, then we need this number, the same number for the oxygen, because this is O2, but this is also O2. But this number, we have seen it before. So this number here, 2.2 10 to the power 22. So we have derived this one. For the chemical water, so this one had only one oxygen here. So the number becomes two times that of the dry oxidation. Because for the dry oxidation, each molecule we have 2 oxygen, but for the wet oxidation, each molecule we have only 1 oxygen. Then the oxidation rate is given by flux divided by N1 value. so that is equal to dx over dt. The x is the oxide thickness. So this one given by f is given by this number here, ks ci. So ks ci, so equal ks times this number here, the 1. So we can ignore this term. So then we do the integration. So we have from here to here. Here we have x here. Here we also have x here. So we need to move this one to the left side. Then we do the integration. We have this formula here. So again, we ignore this term. Then we define b equal to 2d c star over n1, b over a equal to c star over ks n1. A is defined by this one. Then finally we do the rearrangement, so we get this equation. We get this equation. So here xi, this value here, xi accounts for the oxide present at the start of the oxidation process. So here you can see, so both b and b over a is proportional to c star. So we know that c star equals to hpg. So p star equals hpg. That means the growth rate is proportional to the pressure. This is the pressure, pg. So pg is the pressure corresponds to the mean gas flow. So when we have higher pressure, we get proportionally linear increase of the evaporation rate, because this one c star here, they both proportional to the pg. This is the pressure of the gas. So then we can move this term and this term to the right side. So we have this formula here. So here the tau is given by this one. This one we know how to solve it. We learned this in the middle school. So we given by, finally we get this formula here. So here we have two parameters. For b, it's called a parabolic. So this is a square. So this is a parabolic. So b over a, this is a linear rate constant. You can see there are two limiting forms when one of the two terms dominate. For the short time thin oxide, then this one can be ignored. Then thickness is given by this one. So this is the linear regime. For the long time thick oxide, then this one can be ignored. So then we have this formula here. So this is the parabolic. So this one is determined by the diffusion through the citric oxide. So this comes from the flux F2. For this one is contributed from flux X3. This is the chemical reaction rate. So the diffusion is important for the thick oxide. So this DG model is applicable for the case of the oxidation on the flat, unpatterned surface and lightly doped substrate using simple oxygen or the water ambient when the oxide thickness is larger than about 20 nanometer. So the B and the B over A, those two parameters, they both have this Arrhenius expression. This is the Arrhenius expression. So we know B is equal to this one, proportional to the diffusivity. The diffusivity depends on the temperature exponentially. So B over K is the chemical, B over A is the chemical reaction rate. This one also have this exponential relationship. So those numbers, C1, C2, E1, E2 is listed for the three different cases. This one is the dry oxidation. This is the oxygen bubble through water. So this is mostly water. This one is the pure water, no oxygen. This is oxygen hydrogen reacts to form the water. So those are the numbers. So this is the case for the 111 silicon oxidation at the 1 atmosphere pressure. For the case of the 100 wafer oxidation, then the C2 value here, this one, needs to be divided by 1.68. So we will see this later on. So with this one, we can draw the B and the B over A. You can see, you can draw the curve. B, the B over A, and the B, or dry oxidation or the wet oxidation. Then we can calculate the dry oxidation rate from the DG group model. So this is the times, this is the oxidation thickness, oxide thickness. So we assume initial thickness equal to 0. We assume Xi equal to 0. So that means the initial fast oxidation for the first 25 nanometer, is not included. We will talk about this initial fast oxidation later on. This is for the dry oxidation. This one is for the wet oxidation. You can see, for example, at 1 hour, 1000 degree, maybe this time here, 1100 degree, 1 hour, we grew about maybe 0.65 nanometer. Sorry, micrometer. This is micrometer. 0.65 micrometer. For the same condition, 1 hour, 1100 degree. So 1 hour here, 1100 degree. 1 hour here. We got about 0.1 micrometer. So what you can see here, so this is the dry. This is 0.1, this is 0.61. So the wet oxidation is much faster than the dry oxidation. This is as we have seen before. So here's the comparison. So here we compare the dry oxidation and the wet. In this case, oxygen bubbles through the hot water. So for the wet oxidation, it has higher growth rate. But this is because the Hermitz constant. The Hermitz constant for the water molecule is much higher than for the case of the oxygen. It's much higher than the case of oxygen. So we know the C star term has the Hermitz constant here, has the Hermitz constant in it. For the water is this number here, and for the oxygen is this number. Effectively, we can say that the solubility of water in oxide is much bigger than the solubility of oxygen in oxide. That's why the wet oxidation is much higher at the operation rate. So the disadvantage, the wet oxidation, the film is less dense, with more open structures because of the after diffusion of the generated hydrogen along the path, along the oxide. It is typically used for the thick oxide that will not be subjected to any significant electrical stress that may lead to the electrical breakdown. The dry oxidation gives slower, higher quality film than the wet oxidation used for the gate oxide. But again, as I mentioned previously, the wet oxidation is still much better than CVD oxide. It's much better than the chemical vapor deposition oxide. Now, I want to show an example for the calculation for the prediction of oxidation rate, oxide thickness for the different conditions. So here we have 100 silicon wafer has 2,000 angstrom oxide on its surface. The first question is how long it takes to grow this oxide at 1100 degree in dry oxidation. So here we look at this one, 1100 degree dry oxidation. So we have 200 nanometer, 0.2. So this is the time is given by here. So this is how many hours? So 1 hour, 2 hours. Here is 2.8 hours. And second part, the wafer is put back in the furnace in the wet oxygen at 1000 degree. How long will it take to grow additional 3000 angstrom oxides? So the total thickness is 2000 plus 3000, so equal to 0.3 micrometer. 0.3 micrometer. So it is here. So the total thickness is 0.5. This is 0.2 or 0.3, so we have 0.5, so it's here. So 1, 2, 3, 4, 5, so we have here. And here we have this one, the 1000 degree white. So we have this curve here, 1000 degree white. So we have this point here. So total time, so we have this point here. So total time is here. So the total time is given by 1.5 hours. We need, so 1.5 hours to grow 500 nanometer, 0.5 micrometer oxide at this condition. But now we have already 200 nanometer. So to grow this first 0.2 micrometer, so we need the number here. This one is 0.4. So 1, 2, 3, 4. That means we need 0.4 at this condition. We need 0.4 hour to grow 200 nanometer. Then we need 1.5 hour to grow this 500 nanometer. Then the time difference is from here to here. There is a time difference here. This is 1.5 minus 0.4 equal to 1.1 hour. So we need 1.1 hour to grow this additional 3,000 angstrom oxide. You can look more carefully later on. So now let's look at thin oxide growth dependent on the gas pressure. This one I will not talk about this. We know that the C star, HPG. But that means the growth rate B and BOA, both are proportional to the pressure. So the growth rate depend on the gas pressure linearly. And now we look at thin oxide growth. The DO-Groove model provides excellent agreement with the experimental data for the except for thin oxide growth. You can see here, but here is the oxidation growth. This one is the linear. It's linear. This is good. But here you can see at the very beginning, it's super fast. So we have very fast growth. Very fast growth at the very beginning. So to have this curve, so this is the ideal DD-Groove model. So DD-Groove model we have the ideal linear case. But in reality, we find something like this. So to have this curve, we need to assume we're using the DD equation for the thin oxide growth. Thin oxide growth in oxygen on bare silicon wafer. So we need to assume there is already 25 nanometer. You can see here it's not actually like I would say 22 nanometer. A little bit 22 nanometer oxide at the very beginning. Or we can assume the tau is not equal to 0 at the beginning. So you can see if we look at here, we have very fast growth here. So we need to assume xi equal to 25 nanometer. Then we can use the DO-Groove model. So this is the initial growth, then this is the linear growth, and then it's parabolic growth. So here why you see the time is really long, it's hundreds of hours. So this is very long time because the temperature here is only 700 degrees. So normally we do it at 900 degrees or maybe even higher. But when we have this temperature, the time here will become very short. But here we want to show this linear, when you want to show the linear slow growth regime, that's why we use this low temperature as an example. That's why you see a very long time. It looks like very big. It looks like a very big difference, but actually you can see it's only 20 nanometer difference, so not a big problem. But there are a few reasons for the explanation. So here again, this one is 680 degrees, it's linear, but we have a very fast growth. We have to assume we have 22 nanometer at the very beginning. Here are the model to explain the excess growth of the thin oxidation. The first one, there is an electrical field exists around the oxide. Secondly, there is the microchannel in oxide that help in the movement of oxygen to the silicon surface. But this one we know is not true because at the very thin is the chemical reaction limited, not the diffusion limited. The third is the mismatch in the thermal expansion coefficient of oxide and silicon. This causes some stress. But none of these mechanisms again wide accepted. So you do not need to know what is the reason. You just need to know that we have very fast growth at the very beginning. Then the DG model will be good. So now let's look at a dependent on the crystal orientation. The oxidation rate, the KH term. Oxidation rate depends on the availability of the reaction site on the silicon substrate. So the oxidation on the 101 crystal plane occurs higher rate because there are higher number of surface atoms chemical bonds than the 100 plane. So we can look at here. So those are the different 110, 101, and 100. This is the area of the unit cell, silicon atom in the area, silicon bond area, bond available bond area. Then the N, this is the available chemical bond per area. So the N relative to 110 is given by those three numbers. And this is not, if you want to know the numbers here, you need to have know the arrangement of the silicon atom. So you need to look at you need to have a model like this in order to get all the numbers. So I didn't calculate myself, but if you look at the number here, so you can see that so the number density is related to the distance between lattice planes. This is given by, we know that a h squared plus k squared plus l squared. For the plane, for the HKL plane, so the distance between the two lattice planes is given by this formula. So the number here related to this one, but actually it's more complicated because we also need to count the bonds available. But anyway, I will not ask you to do this kind of derivation. You just need to know that the rate for different crystal orientations, they have different growth rates for the Ks term. The Ks is given by this one, so it is roughly proportional to the number of the available silica bonds for the reaction per unit area. As a result, so for the 111 direction, the B over A value, this is the linear growth. The B over A is 1.68. This number, as you see, is not different. If we look at here, so this number divided by this number is given by 1.735. It's a little bit different from the 1.68, but roughly it's close. So the parabolic rate constant B is not dependent on the crystal orientation, because this one is dependent on the diffusion. The diffusion has nothing to do with the chemical reaction. So this effect decreases for the high temperature of the longer time oxidation when the diffusion becomes dominant, as you can see here. So for the longer time, this is the 111 plane and the 100 surface. For the longer time, the difference becomes smaller than for the shorter times. You can see this image here. So this is the 110 growth. It's bigger than 100 growth. The ratio here should be, so this between the 110 and the 110 is a square root of 2, 0.707 is given here. But this number here. So this number here should be 5. So this is given by this number. This one given by this number. So now we look at chlorine-containing gases. So normally when we do the oxidation, we add some chlorine. This can be a chlorine gas, a hydrochloric acid, or the TCE, trichloroethylene, or TCA, a trichloroacid. So why we need chlorine? So we need a little bit. Actually, this helps a lot. First, we have the faster oxide growth because chlorine is a kind of catalyst for the oxidation process. Secondly, we have cleaner oxide, less metallic contamination because chlorine is a metal getter. So we have the sodium or potassium or maybe other metal, nickel or maybe iron or silver. They will form the metal chloride. This metal chloride is volatile. So volatile at about 1,000 degrees. At those high temperature, those metals, they become volatile. That means the chlorine will get rid of the metal. To form volatile metal chloride. So this gives you a cleaner oxide growth, no metal. There is also enhanced dielectric strength, improved silicon oxide interface with lower interface stability that improved device performance. Now let's look at two-dimensional growth, 2D oxidation. We can see in the experiment show that oxidation is slower for the convex or concave corners. Concave corner is even slower than convex corners. So the smaller the curvature radius is, the slower growth. So most here for the low temperature oxidation, and no effect for the high temperature like 1,200 degrees. So you can see here. So first, this one is the convex. This is the convex corner. This one is the concave one. You can see the thickness here, and the thickness here. They are both less than the thickness on the flat surface. So the concave and the convex, they have slower oxidation. The concave is even slower. You can see here. The concave is even slower here. So we got higher temperature here. So this is temperature here, 1,100 degrees. This is 950 degrees. So higher temperature, the growth, the difference becomes slower. The difference becomes slower. So this is because the the oxide can flow a little bit at this 1200 degree or 1100 degree. This is another example. So here, this is the SEM image. This is the drawing. So here we have the silicon here. The black color here is the oxide. So all the black color here is oxide. So here we have a lot of polysilicon. This is the polysilicon. This polysilicon is by the by RPCVD. The low chemical vapor, low pressure chemical vapor separation. It is for the SEM imaging only. So when we have this polysilicon, it's better and easier to show the boundary. But this polysilicon just to show the boundary between the and the silicon oxide. There is no other purpose. So here the inside here, it also filled. It's filled. Here it also filled with polysilicon to show the boundary of the oxide. So what you can see here. So first, the convex content here, concave content here, they got slower growth. Secondly, so I think this surface got more separation than this surface. So thirdly, this concave growth, the thickness here is larger than the thickness. This is the convex. So the concave, the thickness is larger than the convex thickness. The thickness here is bigger. So now this is the 2D growth, two-dimensional oxidation. So we have the corners, 2D growth. So this is the mechanism for the two-dimensional oxidation. First, we have the crystal orientation dependent rate. For example, this is the 2D silicon cylinder. We have 2D. So for the 100, we got thin oxide, then 110. So the ratio here is 0. This is the ratio. This is for the thin oxide. When the KH term, the chemical reaction, KH term dominates. So we have this one. Secondly, now we have two-dimensional oxidant diffusion. That's different from the 1D oxidant diffusion. The third, more important reason is the stress. We have the stress. So because of the volume expansion. So we know that when the silicon gets oxidized, it gets expanded. As the oxide grows, the newly formed oxide pushes out the old oxide. So you can see, this is the newly formed oxide will push out the old oxide. The oxide will rearrange itself through the viscous flow. There will be a stress. So we have the stress. The growth becomes slower. So now we can make use of this. For example, if the cylinder this big, another one. So this is the radius is R1. This one the radius is R2. So which one will grow faster? Which one will grow oxide faster? We can see this one will be faster, but this one have a bigger radius. We have the less stress. So this is the bigger radius is closer to the flat surface. But this one smaller radius, the more stress. So this one give you faster growth. But this one can be used for the AFM tape fabrication, and it is called oxidation sharpening. The AFM tape fabrication. Now I will show you our paper for this purpose. But this is the paper, oxidation sharpening of silicon tips in the atmospheric environment. This is from our group. You can see here. But this is the principle. So here we have the blunt. We have blunt tape. Then we do the thermal oxidation of the silicon. You can see the top part has smaller radius. The bottom part has bigger radius. So there will be more stress on the top part. So that there will be less growth on the top part and more growth at the lower part. Then you use hydrofluoric acid to remove the silicon oxide to get this very, very sharp tape. So we use this simple furnace in the air. We do the oxidation in air, not in the oxidized environment, just in the natural air. So this is the principle. And now we look at the result. You can see this one is the before oxidation sharpening. After oxidation sharpening, it becomes like this. And we can make the tape up to like 5 nanometer sharpness. So the last slide is the dopant-dependent oxidation. So we know that it is found that the silicon dopant, they all tend to increase the oxidation rate when present in a substrate in high concentrations. The effect is particularly important at the lower temperature and for the thin oxide, and is more important for N+ doping than for the P+ doping. Here you can see it here. So here is the different dopant concentration. This 10 to the power 16, 10 to the power 20, and 10 to the power 20. So we have higher dopant concentration. You get we have higher dopant concentration, you get more growth. But you see here, this is not too high. So this is 10 to the power 20. So normally we rarely use this heavily doped silicon. So in reality, so this one is not so important because this you need 10 to the power 20. It's too heavily doped. So there are two numbers. The first is the B dominant. So this is the parabolic term. For the parabolic term, it depends on the diffusion controlled oxidation. So in this case, the dopant concentration in the oxide is important. On the other case, when we have the linear growth rate, then B over A dominate. Then the dopant concentration at the silicon surface, this is important because the dopant concentration on the silicon surface determines the chemical reaction rate at the surface. For the case of this B term, so here I said that the boron will segregate into the oxide and it will weaken the silicon oxide bond structure. This will increase the oxidant diffusivity through the oxide. Okay, thank you.